Okay, in the meantime, I've got my own question. So you mentioned that this can be translated to water waves and acoustic waves, but what about solid mechanic waves?
What sort of waves?
Full elasticity waves. So,
oh, yes. Yes. Any sort of wave will be, they're all, as you know very well, Sebastian, waves obey very similar equations and only differ very much in their constitutive parameters. And elastic waves are very suitable candidates. And of course, their frequencies are low enough that, again, we could modulate the system.
And there is one thing, if you relax this assumption on the impedance, so now you have just one parameter which is modulated, so all this breaks down, or you still have some interesting properties?
If you only modulate one of the parameters, then, as I explained, the bi-anisotropy disappears. But nevertheless, what remains is the amplification and pulse formation process, because you're still dealing with these degenerate forward waves. So some of those slides I showed you for the gain process were actually calculated just modulating epsilon. I didn't explain that at the time. But yes, modulating epsilon alone is a perfectly satisfactory way of getting gain and pulse compression.
So we've got a question from Simon Horsley. So he has some problem to unmute, and he's asking, is there some relation between the amplification in luminal gratings and the work in optical analog gravity? So Simon says he remembers that there were experiments where a strong pulse in an optical fiber induced a luminal modulation of epsilon, and the points where the C modulation equals the C light acted as the event horizon. So I think he's referring to the work of Ulf Leonhardt and.
Oh yes, I'm aware of that work.
So black hole lasers.
Yes. Well, what Simon's getting at there, of course, is the quantum aspect to it, and that's an area which is not much explored actually. So what I've been discussing here is the classical effect, whereby you actually put in some radiation and that is amplified. Of course, in the quantum scene, you have the 0-point fluctuations, and so they're there already. And if you modulate the system in this way, it will certainly pick up the 0-point fluctuations and amplify them. Instance of this is that if you, which is something we're working on at the moment, if you take a surface and you modulate, say, the effective epsilon of the surface, for example, graphene, then you make a grating which is moving across the surface. Then if you make that grating move faster than the velocity of light, then you will create radiation. I wrote a paper about this a very long time ago, about 20 years ago. And at that time, I envisaged a grating which was physically moving. And I hadn't come on to the fact that you don't have to have the grating physically moving. It's enough to have the grating, just the modulation moving. So that's a the real possibility. And that radiation is the analogy of Hawking radiation, where you have an event horizon, which is between, say, two dielectric slabs, and classically you're looking at waves which are traveling almost parallel to the surface, so they're forbidden to get out of the slabs, but they can jump across the grating, across the vacuum gap, and create flashes of light by a Hawking-like process. So yes, thank you, Simon. That's the quantum aspect is very interesting. Watch this space. We'll be publishing on it shortly.
So we have another question. What is the effect of losses in the medium on time-dependent system performance?
Yeah, that's something which, of course, I'm thinking here a lossless system. So if you look at this equation here for the rate of gain of energy, then the losses will be injected at this point here, and instead of having a gain of energy due to an increase in amplitude, there will be a removal of energy by the loss process. So this gain process would then have exactly as a laser does. It would have a threshold, and you'd have to modulate strongly enough that you actually overcame that loss threshold. Something else which I didn't mention in my ideal system is that we've assumed a system which is free of dispersion. And of course, the whole essence of this gain process depends on the light and the grating traveling at more or less the same speed. But if the speed of light varies with frequency, as you pump energy into the higher and higher frequencies of the light, eventually you get to a frequency which will be trapped in the grating and will escape from the grating. So dispersion will also limit how narrow these pulses can be, if not limiting how high they can be. So if you can't inject frequencies which are captured into the grating, then you can't make the pulse sharper.
So we've got a question from Gelsa Barbosa. Are there possible applications in radar antenna arrays?
Maybe. I haven't thought about that. The present trend in radar, of course, is to follow the dolphins and not emit continuous streams of radiation, but to emit very sharp pulses of radiation and hence get a lot more information by looking at what happens to these pulse trains. And of course, these devices do emit pulses, very sharp pulses. So if we get a workable system that works really well, then it might be a great way of doing a cheap, effective radar system.
So he had in mind to apply this to identification of emitters by their frequencies.
Identification of what by frequency?
Of emitters, of sources by their frequencies. I just repeat the question, sorry.
I don't quite understand where the emitters would be.
Okay, so I've got another question. How can we make the difference between the temporal modulation, which is used for amplification, and the temporal modulation, which is used to break reciprocity? So amplification versus reciprocity.
Yes. Well, it depends how fast the modulation is traveling. If you are in the subluminal regime or the extreme superluminal regime, then you don't get this amplification process. And if you inject waves which are sufficiently long wavelengths so they actually don't see the period of grating, then you will have an effective medium. And actually, to have an effective medium, all you need is that there is no backscattering. Of course, under those circumstances, you have no band gaps, and the medium can be described by effective medium parameters. So homogenization works very, very well in the absence of backscattering. But the whole show of an effective medium, as I'll explain, breaks down once you're in the critical region, and you don't have any effective medium parameters there. It behaves as quite a different animal. There are no Bloch waves, you get this pulse formation. So it depends on how fast you make the breaking move.
Okay, thank you very much. Are there any other questions? Sorry, actually, Gelsa Barbosa says, radar emitters that are in the environment, metamaterial slabs could receive those electromagnetic waves and show the emitter frequency spectrum. Well, okay.
That's a rather technical question.
Yeah.
It's probably beyond my radar expertise.
Okay.
So we're thinking here of capturing radar waves and then amplifying them in some way. I think that this system, if people got it going, would be better suited to generating radar waves and sending them out rather than as an amplifier or receive radar waves. But I could be wrong there. Of course, after all, people do, in the traditional way of amplifying radio astronomy signals, for example, is via parametric amplification, which is related to what we have here. So it may be that I don't see the way forward myself, just in generating emitted waves.
So I've got another question. What will happen if there is a phase difference in epsilon and mu? So permittivity and permeability.
Well, maybe I should call on a member of the audience to answer this question. Paloma, are you there? Would you like to tell that story? Paloma?
Yes, I'm here. So what happens actually is that the range where all this localization happens, the luminal range, shrinks. So it's largest when epsilon and mu are modulated in phase with each other, and it gets smaller when they are completely out of phase, but it doesn't totally cancel. So the phase relationship is important, so it has a role, but all these effects survive.
What happens to the effective medium as you change the phase of modulation of epsilon and mu?
What happens to the effective medium?
Yes, outside the luminal range. So,
yes, so the sign of the bianisotropy changes. So when both of them are in phase, you have a maximum of bianisotropy, and then as you start switching out of phase, then bianisotropy is reduced, and sometimes it crosses zero, and then so it's periodically with the changing of phase between epsilon and mu. Is that what you mean?
I've got a naive question. What happens if you start in the first place with a bianisotropic medium and you modulate epsilon mu and the magneto-optic tensor? Maybe this is self-consistent and you know it's
well, I suppose
maintained.
If you didn't like bianisotropy, you could cancel it and make it bianisotropic. But why would you want to do that? Or you could make it even more. So, yeah.
So, in fact, is there anything beyond a bianisotropic system? Can we still augment this, make it even more complex, or it's as far as we can go?
Well, what we have here is just the very simplest system you can imagine. And I mean, my goodness, if I said, okay, forget the time dependence, this is just the Bragg grating, and I'm going to talk to you for 1 hour about the Bragg grating, you'd all switch off immediately. Now, I think you admit that, most people admit that once you introduce the time dependence, even in this very, very simplest Bragg grating situation, you get a huge richness of phenomena. I've described several here. One is the bianisotropy, the other is the localization phenomenon, and then there's the compression of the lines of force, and so on. But that's the very simplest modulation you could do. You could imagine much more complex time-dependent systems. So back to the world of static metamaterials. There are all sorts of structures which people have introduced, which produce a whole range of properties like negative refractive index and so on and so forth. And this is just the beginning. Turn your mind to imagining what time dependence you could introduce, which would be more complex than this. And then you could access all sorts of things like optical activity and so on and so forth. And I wouldn't like to have to prove it, but I think that if you have a time-dependent system, then you could probably mimic all the parameters of the constitutive relations and generate them in some material in some form. I believe that's a true statement, but it's just off the top of my head.
We've got another question from Simon Horsley. He's asking, what happens if you stick an emitter in the grating?
Stick an emitter in the grating? Right. Well, what will happen is that the emitter will become highly asymmetric. The light which it emits in the direction opposite to the grating will be just propagate as normal at hardly the grating, but in the forward direction, the grating will grab the light. Now, there's a point here that the grating only discussed light which travels along the direction of the travel of the grating, and that light, if it keeps pace with the grating, will be amplified. But if you have light traveling at an angle to the grating, of course its direction of travel along the grating, the component of velocity along the grating, is less. And so those components will. So what will happen is that the emitter, which initially produces dipole radiation, will have the forward direction enormously amplified, and the rest will stay relatively modest. So it's a bit like the relativistic emission of an electron, where you have a very, very strong amplification in the forward direction with synchrotron radiation, and other directions are much weaker. So you get this very, very sharpened pulse, not only in frequency, but also in angular direction as well.
So someone has raised his hand. Please come forward with your question for John Pendry.
Yes, can you hear me?
Yes.
Okay, thank you for this beautiful seminar. I have two questions, maybe trivial. The first one is, how do you practically implement modulation in both epsilon and mu to achieve this beautiful effect?
Yes, well, that is an issue. I think in the case of the transmission line, you have the analogy there where the capacitor plays the role of epsilon and the inductor plays the role of mu. Now, you can actually buy relatively cheaply capacitors with varactors which can be modulated, which cost a few cents each, and you can buy inductors which can also be modulated. So that's how you could realize it in a transmission line. Now, you're probably more interested in what we could do in the optical region or in the terahertz region, and there it's really only feasible to modulate epsilon. But the let-out clause there is that the really important thing is that to get a simple theory, you only have to eliminate backscattering. And if you do, if you have a weak modulation, then weak modulations still mix together these forward traveling waves very strongly, but they have very weak backscattering. So you can imagine a system like this where you're modulating only epsilon, but the modulation amplitude is quite small, so you keep the backscattering quite weak, and then you would see all these effects here, except, as I say, for the anisotropy. So modulating exponent alone would produce a lot of interesting effects, and certainly will produce this localization effect I've discussed.
Okay, thanks. And second question, you mentioned terahertz. Actually, when I saw the picture, I think it was slide number 14, where I see a plane wave impinging on a grating, yes, and producing two pulses. I immediately thought about terahertz generation, because this is what I've seen with terahertz antennas, and in that case, semiconductors are used. Would you envisage the use of luminal gratings for such an objective?
Well, yes. I mean, that's the idea with these graphene situations. Emmanuel Gallipi, who's also in the audience, has done some calculations with bilayer graphene, where you can amplify terror. Emmanuel, are you there? Would you like to tell the story of bilayer graphene and your proposal?
Yes. Yes. So the issue we had when we started working on this was when we tried to think of implementation is that most of these time modulation mechanisms are done on surfaces because you have a large surface to volume ratio. The problem is that on surface waves are typically very dispersive. But if you take two layers, each of them with a simple Drude dispersion, and you stack them very close to each other, such that the gap between the two layers is smaller than the plasmon wavelength, then you have a very long linear dispersion regime in the acoustic branch of the double layer system, so that has a linear dispersion. So if you tune the speed of this surface plasmon to the speed of the modulation, then you can achieve the supercontinuum in the plasmon. Well, you can accelerate the plasmon. You can generate a plasmon supercontinuum, and then you can outcouple it if you want to use it for terahertz regeneration, for example.
Okay, thanks very much for this beautiful scenario and contextualization.
No worries. Thank you.
So we've got another question from Emil, I guess. Emil, can you come forward with?
Yes. First, thank you for the very nice presentation. My question is the following. The slides, as I've seen them, refer always to a wavefront which is aligned with the grating. Are there any interesting effects for general waveforms, such as those generated by point sources or other type of sources?
Well, yes. What you have to deal with a point source, like Simon Horsley's suggestion of a point source injected into the grating itself, is that you have lots of different angles of incidence, and there's some interesting effects here in that if you move away from normal incidence, which you have to think about if you have a point source, for example, then one way of thinking about this amplification process quantum mechanically is that because the grating is translationally invariant in the direction normal to direction propagation, you can't add any momentum there. So if you're going to create photons, which you're going to add to the incident photon, then you've got to create them in pairs. And you find that when you inject light at an angle into the system, what it does in fact is produce two beams. It's the time reversed copy of the other, and one is a negative refracting beam and the other is a positive refracting beam. So you actually generate negative refraction in these systems when you think about them quantum mechanically, because to add energy to a wave with finite momentum, you have to add it in pairs with a plus and a minus. Otherwise, you obviously don't conserve momentum, which you have to do even in propagates.
Thank you. Thank you.
So anyone else would like to come forward with a specific question, or we shall just finish this webinar for today?
Okay, thanks, Professor Pendry, for this interesting talk. My question is a little bit similar to
Wow.
well, can you hear me now?
Yes, I can hear you.
Okay. Since the system.
Sorry, you're breaking up there. Perhaps you could type your question in and Sebastian can read that.
Hello. 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 Please, do you hear me? Yes, thank you, Professor Pendry. In fact, I have two questions, please. The first one is about extrapolating what you did to transformation optics to, in fact, to use 4D coordinate transformations and to work in the general Riemannian geometry framework. Hello?
Hello? There's a lot of background noise. I didn't catch your question.
I think this person was asking what happens if you apply this kind of scheme to transformation optics. So you include, perhaps this is what Martin McCall is doing. I'm not sure.
Yeah. Okay. Yes. Thank you for the question. I understand. Of course, transformation optics is traditionally applied to a three-dimensional system. It can, in principle, be applied to a four-dimensional system, where including the time domain. There are problems with that, and the reason is all the things which we see here, in that, for example, in this system, you might think that, okay, you have a grating which is moving less than the speed of light. You can calculate the parameters, constitutive parameters. You can transform away the motion, and you end up with a static medium which has non-isotropic properties, as we discussed. It can be bi-anisotropic, whatever. But that has limited application, because if you then increase the speed of the grating until it's traveling as fast as light, then that picture is totally destroyed, because you then enter a region where you don't have an effective medium, and where you have gain instead, and it can't be described in terms of constitutive parameters. And even with an ordinary grating moving up very quickly, you can get into problems, because you see, it particularly happens when you have a lossy system. In lossy systems, you have a very strict rule which applies to epsilon, for example, and when the system is lossy, epsilon has an imaginary component, and that component is positive imaginary when the frequency is positive, and it's negative imaginary when the frequency is negative. And it has to be like that, because if it isn't, you could extract energy from a system where there's no source of energy. However, all bets are off when you start the system moving, because you then, through the mechanical energy which you have to use to move the system, you then have a source of energy. So the rule that the imaginary part of Epsilon is positive at positive frequencies and negative at negative frequencies is broken. The simplest instance of this is if you have a physically moving system, then the line distinguishing positive and negative imaginary part moves from zero frequency to a finite frequency. And this we mentioned part in our discussions, and this was a source of the dispute between he and myself, which is whether you could have quantum friction. And you can have quantum friction, and it's because you break this rule of always having positive, positive, negative, negative with the real and imaginary parts. Sometimes you can figure that out rather simply, but if you have linear motion, for example, but if you have a complex system, maybe say a rotating object or objects rotating in opposite directions and so on forth, figuring out what happens to this loss process is very, very difficult. And it's something I've looked at, but I haven't come up with a simple scheme of writing transformation optics in a way that's really consistent with loss systems. And I think you have to do this if you're going to make a general theory of it. So yes, in principle, you can apply transformation optics. It often works in lossless systems, but you have to be aware that there's situations where the concept needs some more understanding before you can use it generally. Sorry, a long answer to a simple question.
So in fact, Yi Chen wanted to ask the following question. How sensitive the modulated system is to noise?
Yes, good question. Like any amplifying system, it will amplify noise as well as signal. It will even amplify the noise due to 0-point fluctuations and spit that out of the other end. So yes, you really got to be aware that the system is going to amplify noise, and if you have even a little bit of it around, it may destroy your ability to detect very, very weak signals, for example.
Okay, thank you so much, Professor Pendry, for this wonderful talk. And I would like to remind anyone that you can also watch John Pendry's talk after the webinar. It will be available permanently from tomorrow onwards. And let us thank again and this wonderful talk. Okay, I hope to see you next week again. Bye.
Bye.
Thanks.
Thank you. Bye.
Thanks everyone. Bye.
L'enregistrement a fonctionné?
Oui.
Très bien.